Good morning, everyone. We're just going to wait a couple more minutes for a few people to sign in, but we'll get going in a couple of minutes if you'll just be patient with us, and we'll get going. Okay, good morning, everyone. We'll start the webinar now. Welcome to Picco Engineering's second webinar in our educational series. Today, we're going to feature our project on the Aga Khan Park. And our primary focus today is going to use this as a case study, but really focus on testing and our involvement in the stone testing. So we'll get going. For those of you that don't know me, I'm Mike Picco, and president of Picco Engineering, and we're a structural engineering firm focused primarily on cladding, although we do other structural engineering as well. And today, this is where our focus is going to be on the cladding and the use of stone on the Aga Khan Park. Joining me today as well is Afsheen Khan, one of our structural engineers here at Picco, and I'll let her introduce herself as well.
Good morning, everybody. My name is Afsheen. I've been with Picco Engineering for over 7 years. I share the same passion for cladding as Mike does. My role as a structural engineer in the company is to design and engineer connection, backup structures, keeping in mind ease of installation for the installer. So today's agenda, we're going to go through for the Aga Khan Park. We're going to look at the project background, then project role for Picco, sourcing and testing, and then Picco's role with the contractor. At the end, we're going to discuss some challenges and complexities and Q&A. I mean, you guys can put your questions throughout. We'll try to answer if we can, but at the end, for sure, we're going to try our best to answer your questions. So the project background, Aga Khan, the team members, Aga Khan Foundation Canada, the owner, Charles Correa, the design architect for the Ismaili Center. Fumihiko Maki was the design architect for Aga Khan Museum. Vladimir Djokovic was the design architect for the garden. Moriyama and Teshima are the architect of record. Carillion Canada was the GC. Clifford Masonry, stone installers. Granitex, a stone fabricator, and Picco Engineering engineers and the stone consultants. So these are the architects, Ted Teshima, for the architect of record, Mr. Maki, he's a design architect for the museum, Vladimir Djokovic, design architect for the garden, and Charles Correa, design architect for the Ismaili Center. Inspiration, the light and shadows. As Moriyama and Teshima architects said, that light being the primary inspiration for the project, the building acts as a vessel that is both animated and sculpted by light in myriad ways, casting patterns on the exterior walls of Brazilian granite, enhancing interior space and illuminating the open roofed courtyard. So that being the main inspiration. The concept came from the Aga Khan. He actually wanted the light to be the main concept. He wanted the spaces to be surrounded around as a celebration of light and the mysteries of light, and that nature and the human soul illustrate at every moment of the lives. The concept is particularly validated in Islamic texts and sciences.
Oops.
Afan Park. There are three separate components that make up the Afan Park. The Ismaili Center, the Afan Museum, and the formal gardens with reflecting pools. The Ismaili Center is a representation building for the Canadian Ismaili community that includes the place of worship and various social and administrative spaces. The Afan, Mike, can you go to the previous slide, please?
Oh, I'm sorry. I think there's a bit of a delay.
Sorry, one more back. Yeah, the Afan Museum. It's now home to a collection of Islamic arts and artifacts from across the centuries and collected from Iberian Peninsula to China. So if you've been there, you know what the museum has in store. But if you haven't, that's a must go when everything opens up for sure.
Thank you.
We touched on the Ismaili Center. That's again the place of worship. Formal garden. That's a uniting green space that connects the Ismaili Center and the museum on approximately 2.5 acres of land.
And the project role, Picco Engineering, I guess the architects and ownership group realized very early on in the project the importance of picking the right materials that were going to really bring their vision to a reality. And the whole inspiration around the light and how the light was going to be a big part of the project. They wanted to engage in a process that was going to really select the materials that were really going to enhance that. And we were hired on very early by the ownership group to help them in sourcing and testing various stones for the different applications that they were proposing on the project. So it was approximately a 15-month process from the start of collecting samples from aesthetic purposes to vetting and testing them for the various applications to narrowing it down, and the design team really trying to find a balance between the aesthetics, the technical properties and the performance of the stone, along with the budgets also, because there were large amounts of stone on the project. So it was quite a process that they went through, and the main materials that were chosen were Brazilian granite that was used to clad the museum project, limestone sourced from Croatia on the Ismaili Center, and black granite sourced from China on the pools, and a white granite from China that was also used for the pavers, benches, and planters in the landscaping area. So you can see that stones were selected from various parts of the world, and there was quite a series of different materials that were looked at for various applications. So the sourcing and the testing of the material is the next topic. And Afsheen, if you can maybe run through this.
Yeah. So ASTM testing, whenever specifying natural stone, it is very important to understand the material's inherent characteristics so that appropriate stone can be chosen for the application required. For example, if we are using for the stone for cladding, there are specific tests that need to be required compared to when the stone is only used for pavers. So you don't have to go through all the testing depending on the application of the stone. So as a specifier, the design professional is responsible for material selection based on the aesthetics and performance criteria. he or she must obtain visual and physical samples and acquire the test results and backup claims about the material's performance for the particular application. Now, it is recommended that ASTM test results are not older than 3 years, but in some cases, historic data can be used, again, depending on the application. It may not be as critical to have the most up-to-date data if it's only used for an interior bathroom facade or bathroom cladding. Natural stone is anisotrophic, which means physical properties like strength, durability, and resistance to the natural eroding elements like water may vary depending on which direction it's measured. And ASTM does provide the guidelines and the number of samples to be tested, like for each application. The ASTM testing, these are the most commonly used test standards relevant to the natural stone. I'm just going to read them out, what they are, and then we can elaborate what are the importance of these tests. So ASTM C97, the absorption and bulk specific gravity of dimension stone. ASTM C170, the standard test method for compressive strength of dimension stone. ASTM C99, the standard test method for modulus of rupture. ASTM 880, the standard test method for flexural strength of dimension stone. ASTM C1353, standard test method for abrasion resistance of dimension stone subjected to foot traffic using rotary platform double-headed abrasure. ANSI DCOF, that's the dynamic coefficient of friction. ASTM 1354, strength of individual stone anchorages in dimension stone. And ASTM C1201, the standard test method for structural performance of exterior dimension stone cladding system by uniform static air pressure difference. So ASTM C97, that's the absorption and the bulk specific gravity of dimension stone. So the absorption is the measure of stone's porosity. The characteristics is an indicator of both its stain resistance and possibly its performance in cold, wet environment where it will be subjected to freeze-thaw cycle. This test also gives us the density of the stone, which is used in all our calculations whenever either the stone is stacked or individually load-bearing connections are used for those applications. ASTM C170. Now this test is the method of compressive strength of dimension stone. It measures the stone's resistance to crushing pressure. It's particularly important when we are using stone as structure. When stone is stacked for 1 story or 1.5 story on each other, so it becomes really important to know what the compressive strength of that stone is, so that appropriate height can be stacked within the safety limits.
Yeah, another, if I could just add, Afsheen, is stone is starting to be used a lot more as a structural element. And with sustainability becoming very prominent in design now, we are utilizing stone as a structural element a lot more. For example, solid stone columns on porticos supporting potentially steel framed structures above, or different elements that we actually use the stone as the structure without using a steel column, for example, to core through the column and cladding it. So this becomes a very important measure of the stone's capability to take whatever loads are being imposed on it. And we'll get into safety factors and how they play a factor in it later. And incidentally, our next webinar coming up next month will really focus on stone as structure. And we're going to show a lot of examples on where we've used stone as a structural element, and in some cases, entire structures of stone, and where it's going in the future too. So if you're interested in that, our next webinar will be focusing on that. And just a little aside to this test here, that becomes very important in that application.
So the next one is the ASTM C99, the standard test method for modulus of rupture. This test measures stone shear strength and bending resistance, generally used for stone greater than 2 inches. This test method and the flexural test method are interchangeable depending on the application. We may need either or sometimes both are required. ASTM C880, the standard test method for flexural strength of dimension stone. This test evaluates bending strength using 2 point of loading and a sample that is actual thickness of the stone to be installed. So you basically test the stone flexural dimension for flexural strength based on its actual dimension. Let's say the flexural strength is, the stone is used for just 1.25 inches. We will only use that thickness for that particular project to test it. And as we are going and changing these facades, more and more thinner stones are utilized in all these buildings, and this test becomes really important in order to come up with an actual safety factor to be used for safe installation. The ASTM C1353 standard test method for abrasion resistance of dimension stone subjected to foot traffic. Now, this test determines the degree to which a stone material can withstand scratching or abrasion. ASTM testing still, but this one is an ANSI dynamic coefficient of friction test. This test measures the slip resistance of an object in motion. ANSI 326.3 states that hard flooring surfaces in level interior spaces that are expected to be walked on when wet shall have a dynamic coefficient of friction of 0.42 or greater for safe installation. ASTM C1354, the strength of individual stone anchorage in dimension stone. Now, this is one of the most important as the C880 test, the flexural strength test. This test evaluates the performance of individual anchor with a specific stone product. You can actually see from these two pictures. The picture on the left is a stone pin, a pin connection installed into the stone, and the stone, the picture on the right is a kerf connection, and you can see this is tested all the way till failure, and all those numbers are recorded for a number of samples. And once we get all the data, we evaluate what kind of safety factors can be utilized in these stones.
The ASTM 1201 test is a full panel test, and this one here is used in some applications where we want to test the actual assembly that we're proposing for the job. So you're getting the information from the flexural strength of the stone, you're getting the information from the anchors. You assemble a full-scale panel with an airbag put in behind it to simulate wind pressure on it, and you load the panel up. And what it will do is it'll demonstrate the mode of failure. We'll take it up to whatever load it fails to, and again, it's another measure of the safety factor for the entire assembly. And what we usually do in this case here is when we have materials that may have variabilities with respect to veining in them, and sometimes the flexural strengths may show some lower failures at some of the vein locations. And what we try and do is get some panels that show the different veining in them, and we can load them up and see whether this effect of the vein, what the effect of the vein has on the assembly when it's loaded uniformly on the panel. So you can see two examples here. The one on the left is a long horizontal with connections top and bottom that would get loaded up to failure. And in this case here, the failure actually occurred at the connection locations. And on the right-hand side, you can see another assembly where the actual panel failed in this case here. It failed in the middle, but the anchors were still holding the panel in place. So this is, again, another very important test. The other thing that's also very important is mock-ups. And mock-ups can be various sizes and for various reasons. Aesthetic mock-ups are one thing to actually see the variation of the stone within the assembly. You can establish certain parameters with what's acceptable from visual perspectives with regard to the stone. And it also tests the installation on more complex installations. How easy is the connection system? How much adjustment is in the connection system? Is there enough adjustment in it? So these are all things that can be monitored and adjusted during the mock-up stage if there are any issues that are identified. The two pictures on the left are the actual mock-ups of the Eisenhower Memorial in Washington, D.C. There were these large round columns with bolted assemblies. You can see the metal framing there. And again, this was a mock-up just to check the feasibility of how to install the anchors, the sequence of the installation, and who had to go first to access certain things. And the one on the top is some other complex geometry challenges that were going to be encountered on the job, along with some paving. So these mock-ups actually kind of covered all the scope in the project, and we were able to check the feasibility of the anchor design and fit and adjustment and also aesthetics in that phase. The one you see on the right is actually one of the corner mock-up of the Aga Khan Museum. And again, this was able to check the aesthetics of it along with the installation procedures and how that whole process was going to work. Another thing that becomes prominent on much larger projects is full-scale mock-ups, where you're actually testing the air and water penetrations, assemblies, caulking, sealing, pressure diff. You can create pressure differentials within the interior and exterior space. And here's some examples of a few of the projects we got involved with. The one on the left is the Air and Space Museum in Washington, D.C. And you can see this is testing the glass assembly integrating into the stone wall. And we actually tested it with driving rain with a negative air pressure on the inside. So it had a negative pressure that would allow kind of a sucking action on the water. So it was monitored to see how much the whole system could perform in that system. The one on the right is another project actually that Afsheen was involved with the engineering on, and actually went down to witness the mock-up testing. And maybe Afsheen, you can elaborate a little bit on that one.
Yeah, for sure. The two pictures on the right, that's from a project that we did. It's a courthouse in Portland, Oregon. But this full size mock-up was tested just because of obviously one for what the reasons what Mike said, for all the water and the sealant and all those testing, along with it was a performance mock-up. Seismic in Portland is the main consideration. So we were given the drift criteria of 3-inch of drifting in between floors, and there was like a 17-foot height floor to floor. It performed extremely well. How the whole system moved as a racking, and up to 3-inch, we hardly saw any cracking in the stone or any joints getting too close to each other. We actually tested it to 4.5 inch with a very little failure, joints closing in the end. And again, this proves that once you do the testing and once you actually use proper safety factors, this can be, the cracking and breaking of the stone can be avoided significantly.
Yeah, it was very interesting, and we were actually pleasantly surprised at how resilient the system was with that much racking in it. And it's hard to see here, but the joints were actually opening and closing, and the corner connections were designed in such a fashion that the corner could kind of swing out and come back in with the assembly. So we created a pivot connection on the last panels in the corner that allowed the whole system to shift and pivot on the corners and come back in without jeopardizing or crushing the stone on the corners. So it was very, very successful application of that. And Afsheen played an integral role in the design and engineering of that.
Now, the test results and the selection of safety factors. Once the test results are received, we interpret the results, see what the variation of the results tell us for all those different samples, and then we assign an appropriate safety factors. For example, depending on the coefficient of variance of all the test results we receive, the safety factor could be anywhere from 5 if the coefficient of variance is 10% or less, to a safety factor of 8 if the coefficient of variance is 20%, or to 12. Now, it all depends on how variable the material is and what kind of test results are we getting. So if you see the table on the right, we have highlighted in yellow the BSI best practices. It actually gives some guidelines for minimum safety factors based on the CV, the coefficient of variance. Sometimes we see in specs that a safety factor is asked for a specific stone. For example, that minimum safety factor is supposed to be 8. And that could be true for some applications or for some materials. For example, if you're using a limestone or a sandstone compared to a granite, you would not need a safety factor of 8 for a granite due to its inherent stronger characteristics. So these are, at these points, that's where these tests become really relevant, where we can either increase the safety factor or reduce the safety factor, and at the end, it can be very beneficial to all the stakeholders, saving material, saving over designing, and all those things.
Mm-hmm. Very good. So as Afsheen mentioned, these are kind of guidelines based on historical data, based on different types of materials. So as she mentioned, you can see how the granite is generally a lower safety factor than some of the other materials. Granite, being an igneous stone, is basically fused together a little more strongly than some of the metamorphic or sedimentary stones, which are the other ones, which is why, generally speaking, the safety factors are a little higher in some of those materials. So these are used as guidelines. And as Afsheen mentioned, the more data we have, the better we can reflect really what the appropriate safety factor is for the actual material that we're using. So I'm going to delve a little deeper here with an actual example on 2 different materials and the series of tests that we have. So here we're testing for flexural strength. And we can see when we look at the values, the mean value, which is the average strength of these 2 materials, we can see that they're very, very similar. One having a flexural strength of 1,018, and the second one having a flexural strength of 1,006. So in many cases, when we ask a quarry for data on their material, they would provide us with the average strength of that material. So we could have, in this case here, 2 different limestones, both having relatively equal flexural strength. We both received the data, 1018 and 1006. We can design these materials basically in a very similar way if this is the only data we have. So let's look at a little deeper now, and how do these two materials compare to each other when we chart the test results in a graph. Here's the graph of the two materials, material A being the blue line and material B being the orange line. What this is demonstrating is right now is we can clearly see that material A is a much more consistent material. Material B has values ranging from 1400 psi to below 600 psi, but the average strength of both materials comes out to be almost the same. What this graph clearly shows us is you can't design these two stones the same way, even though their average strength is the same. So that's where the coefficient of variation comes into play, where material A has a coefficient of variation of 7, which is very consistent. Material B, quite variable at 29, reflects two different groups of safety factors for various materials. What this allows us to do is, one, ensure safety. If we're using material B, we obviously need a higher safety factor. If we're using material A being a more consistent material, it allows us to design to a smaller safety factor, which is designing efficiency into the system. We're not unnecessarily adding safety factor just because of the material class that it's in and the recommended safety factors. So the more data we have on testing, especially with larger projects, it can actually result in a lot of saving to the project by having this information. So I hope, we're getting into pretty technical material here, but I think it's a very clear demonstration on why these test programs are very important, especially on larger projects, to really get appropriate data to do a proper, efficient design and safe design on the system. So I think this clearly demonstrates that. Just to give you a sample of some of the stuff, some of the materials that were investigated on the Aga Khan Park, from sandstones to marbles to granites to limestones, a whole bunch of different materials were selected, and they were different color palettes and different ways that the light reflected on them. So a whole gamut of material was investigated and tested. The first group of samples were collected based on aesthetics. Then after the first set of testing program, we vetted out a bunch of material that wasn't going to work because of technical issues. And then as it got narrowed down, the testing program grew with the smaller sample of the materials that were made the short list. And at the final selection, we can see that a limestone for the Ismaili Center was selected for the cladding, the Dalma cream Croatian limestone, the Brazilian granite, the Margarita White Brazilian granite was chosen for the Aga Khan cladding, and it was actually, I believe it was a sandblasted finish that really allowed the crystals to really shine in the light and create a really nice effect. In the reflecting pools, a black granite was chosen, and you'll see in the photos that we show you later the effect of having that black surface on the reflecting pools and how it really creates a mirror finish. This material here was obviously chosen to be a highly durable material because it was going to be subjected to water all the time and a lot of freeze-thaw cycles. And the same thing with the material chosen for the pavers, planters, and benches. It had to be a very durable material because it was going to be exposed to the elements a lot and horizontal surfaces. And these were the final selection of the main materials on the project. So after we finished our scope with the owner group in helping them vet and select the materials, we were then hired by Clifford Masonry to do their engineering on their anchoring design. Afsheen, maybe you speak to
Yeah.
we played with Clifford on the project.
Yeah, so once we were hired by Clifford, the main goal was to provide the connections which are simple to install and will cover most of the conditions based on the variance of the concrete in and out. All the connections needed to be very robust at the same, so that all the joints that were designed can be achieved at the same time. And we went and we came up with a really cost-effective solution with 2-piece connections, in some case 3-piece connections, in order to install this complex geometry. So we provided these kind of concrete concrete connections with 2-piece connections at the corners, and this shape was not just going in, it was going out on either side at the corner. So in order to keep one connection, there were slots provided in both these plates in order to make as little connection or plate sizes as possible to mitigate issues on site. You can see here the D4 connection, it's a 3-piece connection. So the main connection is at the back, the angle, and then another plate comes at which has the tolerance of in and out, and then a liner plate at the back of the stone. Same thing at D1 and D3. These were two-piece connections. D3, as you can see, how the geometry of the concrete and the shape changes. So in order to make that all installation easy, the angles were bent, or the plates were bent in the same angle as the wall, concrete wall. And you can see from these pictures, oh, go ahead. These pictures, when we did the installation, all these connections had to go all the way to the back where the concrete is, with the backup structure. And the insulation was dealt with during this by cutting out blocks and installing the anchors directly to the concrete, and then replace the insulation. And you know, they installed the foams and the blocks back and taping it to ensure the proper seal. Now the challenges and complexity. This is the mock-up that we showed the picture of in the previous slides. We did this mock-up, and as you can see, the 3D shape of this corner, how it goes in and then out, and then outside the corner as well at the same time. So this one, in these kind of cases, it does require special testing sometimes to deal with the complex geometry, and that's where the ASTM tests come really handy, and we can get these as a full-size performance mock-up or full-size anchorage testing mock-up done on site. There's another mock-up corner drawing, how it came about. Like, you can see all these joints, and because the Archon was really particular about each and every detail of the project, the joints were very important, that they were all kept the same. All these stone tickets were unique because of the changing geometry from in and out, and then back into the structure. So Daniel Teramura, the partner in Moriyama Teshima, he said that I don't remember any other client who has taken that kind of interest in the details as Mr. Agapan did.
Mm-hmm. Yeah, apparently there were stories that he was visiting the site quite regularly, and being quite critical of some of the details. So he was very, very engaged on the project. And I think it was a testament to him and a testament to the team that if you've been to the place, you can recognize the level of detail and care that was taken by all the stakeholders in both the design and the execution. And I think the pictures speak for themselves. We'll just run through some of the photos of the finished part now and kind of demonstrate what we're talking about. And it's quite a spectacular place, both interior and exterior. If you do get a chance to go and see the museum on the interior space, you really get an understanding of their focus of how light played an important role with all the different ways that they're allowing light to come into the various spaces. And there's a courtyard right in the middle and some of the skylights. I mean, understanding some of that vision that they had and walking through the space, you can really feel how that was an important aspect of the design and how they really pulled it off. Here you can see the reflecting pool and how everything reflects off it, and just the way it creates, you know, the landscaping and the buildings, the way they dance with the reflecting pools and the landscaping. Here's another shot again that demonstrates the same thing. This is a shot from the museum side towards the Ismaili Center. And this is from the other side back toward the museum. And again, you can see how the reflection is really quite spectacular. And then the way the shadows and the shape of the building and the way the shadows are cast on the building and at different times of the day, it just has quite a different look. Here again, some of the landscaping features. So the granite border around the planters and some of the benches that were all natural stone. And here you can see again how the shadows are playing on the corner of the building, one side in the shade and one side in the light, and how that changes during the course of the day. And then at night, I mean, the lights and the way the light reflects on it at the nighttime is quite spectacular too. Here's a few other views of the finished product. And that ends our presentation today. So I encourage anyone, if you have any questions that you'd like to pose right now, please add them in. There's one question I think that was addressed at some point, but I'm not sure what it was referring to. It's referring to acceptable alternate question mark. Maybe if you can elaborate on that, we can try and address that now. And if anyone has any other questions, please feel free to forward them to us. You can send them to us at the emails here if you like. And our next webinar, as we said, is next month, and it's going to be on stone as structure. And we actually have a couple of special guests that will be joining us on that are going to speak to that, and we'll be promoting that as well. I want to thank everybody for participating in the webinar today. I hope we shed some light on the testing aspects of stone. Our goal is to each webinar that we're going to present is kind of offer another educational part of the stone industry. So we'll touch on different topics, whether it be BIM technology. Next month is using stone as a structure. So we're going to create a series of webinars that hopefully will be educational in nature, and we'll encourage you. And if you do have any topics that you would like us to address or include in any upcoming webinars, again, please feel free to send us an email, and we'd be happy to try and answer them for you. I'm just going to try and get to a few of the questions here. Let's see. No, I don't see any questions, so I think on that note, we'll end the presentation. And again, thank you all for being with us. And oh, actually, here's a question that just came in. Let's see if I can. I didn't see ASTM C97 consideration for moisture in the Portland project. No, I'm not sure actually. Afsheen, can you address anything on that? What the Portland?
C97, like this stone was already vetted out from a lot of stones that the architect chose. So that was already like taken into consideration. What kind of stone would be best suited for that particular project?
Okay. Yeah, I mean, usually we'll, I mean, the C97 and some of those tests would be done earlier on. We would get all that data. When we get into full-size mock-ups, it's really usually just on performance. So the stone's already been vetted at that time. All those measures are taken. And really at that point, it's more air, water penetration that's being measured. And in this case here, performance on the system for the seismic loading on the rack and the racking of the assembly. So
yes,
I hope that answers your question.
One more thing on this one, because this was a rain screen system, the moisture was not such a big issue on that one because everything was an open joint, and due to the rain screen, the water was supposed to go and in the back of the wall and flow out.
Yeah. Actually, another question came in as well regarding ASTM 666, which is the 666 test is actually designed for brick, for freeze-thaw resistance of brick. It is utilized on some stone testing as well as a measure of rapid freeze thawing. And how we usually apply that test is very often, if we're using it to measure strength in cladding, we will use this test on the flexural strength samples. So we'll do a baseline test, dry and moist. We'll get that baseline data, and then we'll run the similar samples through freeze thaw cycles under the parameters outlined in C666, and retest those samples on flexural strength. After, usually we'll take them to 25 cycles, 50 cycles. Then depending on the results, we may go to 75 and 100 and measure the flexural strength after these cycles and chart the drop in strength. So then that would give us a measure of how much is the stone losing in strength after so many freeze thaw cycles. So good question. It's not actually a stone test, so it's not listed in the stone testing ASTM tests, but it is a test that is applied to freeze thaw measures in the stone testing as well. So thanks for bringing that up. And I think that's all the questions right now. And again, thank you all for attending, and we hope to see you again on the next webinars. Thank you very much.
Thank you very much.